Okay, so my talk's going to be about hyperparameter optimization. And I'm going to explain a little bit about what hyperparameters are and why you should care and why we might want to optimize them. I'm going to try and tie it in a little bit to what Hobson and Zeke were talking about. And I'm trying to make this pretty introductory. I might not be the best judge of that. So if you have any questions, feel free to stop me at any point. Just ask. So starting with the question of what is hyperparameter optimization, we might want to first ask, well, what are hyperparameters? One way to think about them is that they're like the machine learning model's knobs. And for an example of this, is everyone here, are you guys familiar with gradient descent? Have you heard of that before? Yes? No? Gradient descent? Okay. So let's say I have this picture right here, and this is like some shape, okay? And I start at some point on the shape, and I want to try and get to the lowest part of the shape. Well, naturally, a good, nice algorithm for this might be I stand at this point, and I look around in a circle, and I say, okay, whatever direction goes the most down, whatever that means, I'm going to take a step in that direction and then repeat. And the idea is that hopefully I'm going to end up lower than where I started. Now, whether I'm going to end up at a global minimum versus a local minimum really depends on what the shape is that I'm on and where I started. But this is what gradient descent is. So in the context of machine learning, the idea is we have a bunch of parameters or a bunch of weights in the case of a neural net, and we're trying to learn the parameters or weights that output something that's very, very close to what we want to output. In the case of neural nets, or a linear regression, in a lot of cases it's just the weight times the input plus another weight times another input. That might just be some linear function. And we're trying to learn the weights that map the inputs to the correct output. So that's what a machine learning model is. In the case of a hyperparameter, what we're actually looking at are the weights that we initialize our machine learning model with. So coming back to our gradient descent, the parameters are where we start. That actually determines the space. And you might say, okay, well, why would parameters actually give us this weird space? Well, it really depends on what is our metric. How do we say how close our predicted machine learning output was to the actual output that we wanted? And by defining that loss function or metric, we get some distribution or shape. So in this case, maybe we have an x parameter and a y parameter, and then the loss function given those x and y parameters gives us the z. And of course, if the loss is close to 0, then we're very low. And that's where the shape is coming from. So coming back to our gradient descent algorithm, if we're standing at a point with some parameters, and we're looking all around, and we take a step down, that's the machine learning. The hyperparameter part of this is how far of a step do we take? We need to decide that before the model, or we need to decide how we're going to decide that before we start running our model. For instance, if you have a bunch of sharp drop-offs, like cracks, that you could easily step over if your step size is too large, you're just going to totally miss all the global minimum, or even the local minima, and you're just going to see everything's flat, right? But if you make them teensy tiny, of course you're going to converge to local minima, but it's going to take forever. So finding that balance is really important for the success of your model. And some other examples. So just to summarize, the parameters are what the machine learning algorithm learns. The hyperparameters are how we initialize the machine learning model. And another way to think about hyperparameters are some hyperparameters determine the complexity or the flexibility of the model. For instance, if we take really small steps, then we are much more capable of kind of walking over a very complex terrain and having a good idea of how the curves work. Whereas with larger steps, maybe everything will look relatively granular and flat. Another really common example of a hyperparameter is a regularization parameter. And regularization exists to try and limit the amount of complexity. And the way it does that is that if we have a bunch of weights that we're looking at in our model, we might say, okay, well, we want to prefer models that are simpler rather than more complicated, so we don't overfit. So we're going to add a penalty term to having more models. And an example of what a penalty term looks like is maybe I'd say, okay, plus lambda, this is to m, where m is the number of training samples, times the sum of the weights that I initialized it with. So if I have this large lambda, lambda large, in this case, and this is my loss function, by the way. So we have the normal loss function here, plus this little part at the end, which is going to be our regularization. So what this does is, okay, when we run our model, given our weights, this part right here is going to say how close we were with our predicted versus the actual targets. And then this part over here is going to say, okay, with all our weights, when we sum up them, if lambda is large, then we're going to really want to have our weights close to 0, which is good. We wouldn't want a lot of weights. That would overcomplicate the model. Whereas lambda is very small, then we don't care if we have a lot of weights. That's not really going to contribute very much. So in this case, lambda is called the regularization parameter. And again, just to summarize, that's to prevent overfitting, simplify the complexity of the model. So some examples of this in decision trees that Alan talked about before, maybe the depth of the decision tree, how many ways we cut up the space, or the number of leaves in the decision tree. So you could have a decision tree with very, very deep, that learns all the characteristics of your individual data set, but it doesn't generalize very well at all. So by limiting the depth, we simplify our model, and then it makes things a little bit more generalizable. So for SVMs, misclassification penalty term, how much do you penalize something for classifying something wrong, kernelized SVMs, how we set up the kernel. The other case is hyperparameters affect how the algorithm learns. So the step through for gradient descent also works in this case because, of course, if it's really, really small and granular, then it's going to learn a lot better. Some other examples is convergence thresholds. At what point do you say the model is good enough versus no, it should keep on learning? How close do you actually want to get? How much should your answers converge before you say, okay, we're done here? For random forests and boosted decision trees, having the number of trees that you're going to run these decision trees on and aggregate is another question of how your function learns. So now that we have an idea about what hyperparameters are and what the difference is, on to hyperparameter optimizers. So Bergstra, who is one of the pioneers in this field, describes a hyperparameter optimizer as a functional from data to classifier. And the key that I was trying to make here is that we can think of hyperparameter optimizers as things that take in data and then output a model. So for machine learning, usually machine learning takes in data and then outputs a prediction or some parameters or something like this. This actually takes a step up, inputs the data, and then outputs a machine learning model. So let's try and make a hyperparameter optimizer. So we have all these hyperparameters, and we want to find out what combination of hyperparameters actually gives us the best models. So if we thought about having just two hyperparameters, we could say, okay, well, they better not depend on each other, so we can think of them as a grid. I'll say theta 1 and theta 2. And then let's just cut this up like so, and then...
So like number of neurons and number of layers.
Yeah, that's a great example. Yeah, and then we can just say, okay, I'll try out this, and then just sample a grid of hyperparameters and see how the models do in each case. So this is exactly called grid search. Really good thing about it is that since our hyperparameters don't tend to depend on each other in most cases, it's super parallelizable, which means you can run it pretty fast on a big computer. The bad thing is that it's literally brute force, and that means it's not super smart. And the really bad thing is that it might not even find optimal values. So the reason for this is, by the way, here's our example where we might have a unimportant parameter that doesn't really affect our model performance very much, and then the x-axis is a very important one. And in this case, we've actually flipped it where we're trying to get to the maxima, not the minima in this one. The sizing, the spacing of our grid is actually so large that we've missed important features. So we've lost that granularity, and we've actually completely avoided the most critical part to the whole hyperparameters. So now we need to come up with a solution. Now, we might say, well, what if we actually just randomly sampled from the parameter space? Would this be a good idea? Would this be a bad idea? And it turns out, actually, this is a really good idea. Random search was written extensively about by Bergstra and Bengio back in 2012. They're the ones who really had convinced the machine learning community to start using random search. And let's see why it's a very good idea. So one of the issues with grid search is that when we have lots and lots of hyperparameters, that means volume grows exponentially with the number of dimensions, which means that the number of hyperparameters that we need to sample over is going to grow exponentially. So that doesn't really scale well. Whereas for random search, it turns out that the number of necessary samples is actually quite small in order to well characterize a space. And furthermore, there's this really nice property that was discovered, which is that data and higher dimensional data actually tends to have lower dimensional forms that are pretty authentic. So what I mean by that is that very high dimension of variance is retained by dropping into lower dimensions. Another way to think about this is that, surprisingly enough, data in very high dimensions tends to conform very well to a lower dimensional manifold or weird shape if you're a mathematician. So that's another surprising reason why random search works. But let's try and figure it out using some really basic statistics why maybe intuitively random search is a good idea. So let's think about how many times would we need to sample randomly to get a reasonably close to an optimal configuration. And to make this a little bit more quantitative, I'm going to say, let's say we want to get on n successive samples, we want to get at least one of them to be within 5% of the optimum. And we want a 95% probability that we actually got there. So this might sound complicated. I'm going to work you through it. So the first step is we want to define the probability of a miss. And if we're trying to get within 5% of a global optimum, then the probability of missing that is 1 minus 5%. And the probability of n misses is just going to be the product. So then the probability of a hit then, on n successive times, is going to be 1 minus the probability of the miss. And we wanted 95% confidence, so we set that equal to 0.95. Now we have an equation we can solve for n, and we find out that actually n is pretty much 60. So to summarize, that means only using 60 samples, we have a 95% probability of getting within 5% of the global optimum.
Where one sample is a full chain model.
Exactly.
Yes.
Yeah,
Exactly.
they're expensive.
Very
Cool.
expensive, yeah. Except a lot less expensive than doing
Yeah.
grid search. That's the key.
True, touche.
So now so that's a probabilistic there's a few assumptions that I made there in the background that you can think about. I'll leave it as an exercise to the viewer. But luckily we have these things called computers and machine learning libraries, so we can actually do a bit of, and here's an example of random search compared to grid search. You can see actually it's hitting that global optimum right there.
Amazing.
Yeah, very nice. This is from Bergstra and Bengio's paper introducing random search. I highly recommend it, and I also have it in the bibliography of this slide. All of their papers are actually really accessible, not super out there. Anyway, so what I'll be taking you guys through is a simple example of how to implement these two different types of hyperparameter optimizers using scikit-learn. and then we can benchmark them against each other and see how they actually play out in real life. So first, we're going to be importing some stuff, and I want to reiterate, Anaconda is really great. Anaconda is a bunch of open source Python libraries, and it comes with this Conda package manager, which allows you to, so when I was making this project, for example, I made a new virtual environment using Conda and automatically loaded it up with all the machine learning stuff that came just by saying Conda create environment, hyperparameter talk, Anaconda, and then automatically I got all of the scikit, all of the NumPy, everything, and it's really great for doing scientific Python. Highly recommended. So anyway, we import some stuff. The key right here is that we're going to be using the random forest classifier. Here I'm importing grid search and randomized search, and then from SciPy stats, I'm importing randint because we're going to be drawing a random integer from a Gaussian distribution, and that's for the random search. So we're going to be using the iris dataset, which we used before. Flowers, not eye things. And here we go. That's all it takes to load it up from scikit. Next, we're going to be making our classifier. The really nice thing about scikit-learn, it's literally just a line to create a machine learning model. That's really great. This report right here is just going to be a helper function to output some useful stats when we run our model search. So this is what I was saying before. We're going to be sampling from a Gaussian distribution. There's actually a ton of different statistical distributions which you can use for different modeling purposes. Here I'm setting up the parameter distribution. For max depth, it's just going to be either try 3 or try none. Here, pull some integers. So in any case where we could set it up as a distribution, I do. And in other cases, we only had a binary choice, so I just set it as an array. Finally, we're going to run it. Running just means we're going to have this functional right here, the randomized search, that takes in the model, and it takes in the distribution, and it's going to output some performance and say which model was the best. So the model was already initialized with the data, just to point it out. So it's actually really taking in the data implicitly.
Did you put this notebook up somewhere?
Yeah, it's on my GitHub, which I'm linked to. So also I'm going to just do a start and finish time so we can see the execution time on my system. And here we go. When I run it, we get a few different scores. We get around 92, 91% accuracy. And that was for 20 candidates, and it took around 4 seconds. Okay, great. So now let's try it for grid search. Grid search, same thing. The only difference is there are no distributions I'm pulling from, just sampling arrays. And once again, I'm going to run the start and finish times, and when I run it, okay. So we got pretty comparable, 93% accuracy, great. But this time we sampled 216 candidates and roughly 40 seconds. So what we can take away from this is random search took around 4 seconds, grid search took 40 seconds, random search sampled 20 candidates, grid search sampled over 200, and it was really comparable performance. Now, all of these different machine learning models work by taking a pseudo-random seed with which to seed the model with. So depending on when you run it, you can get different answers each time, and the performance will get better or worse. But in pretty much every case I've run, and you can run this over and over again, they're going to be pretty much comparable. The random sampler actually comes out a little bit on top over lots of different trials. Okay, so that was my talk about comparing randomized and grid search, but what about if you want to learn more about HPOs? Well, first of all, I'd highly recommend the scikit-learn docs. I'm going to be putting this talk up on, it's already on my GitHub, and it has lots of links. That's what all the blue stuff is. Once you get past those, highly recommend reading the original papers. These guys are doing cutting-edge stuff. Algorithms for hyperparameter optimization is a paper by Berkshire Bengio and others. that goes over a lot of the really big advances in the field. And HPOlib is a library that has a Python wrapper on it, and that goes into some more advanced hyperparameter optimizers, including the SMBO, which is something, what is it? SMBO, something global optimization.
Sequential
Model
order.
based, yes, sequential model-based global optimization.
That's it.
There's also ones that include sampling functions from Gaussian processes and crazy stuff. And by the way, if you're looking through all these hyperparameter optimizers and you're like, why is this math so nuts? Well, the reason is when a hyperparameter optimizer takes in machine learning models, it can't know what the machine learning model is, because it's supposed to be taking in basically a black box. And so the issue here is with machine learning models, this is kind of an aside, but so machine learning models, assuming that we have a target data set and we're trying to train it by getting close to that target data set, we have this loss function, which is the metric of how well we've done. And the way we tend to say, get close to that global minima is we say, okay, we're going to take the derivative of loss with respect to the parameters. And we're going to try and get close to 0. That's just saying find the global or local optimum. The problem here is if you don't know, I'm just taking the partial derivative with respect to each of the parameters of the model, setting it to 0. The problem is if you're treating your machine learning function like a black box, or for instance, you don't have a good idea of the metrics that you're going to be plugging in ahead of time because that's what you're testing, then the derivative isn't necessarily well defined. And so you have to think about things like derivative-free methods for analyzing these black box machine learning systems. And that's why these advanced hyperparameter optimization schemes get really complicated. But they're also really fun and super cool. And then finally, Total Good. Hobson, Zeke, and I and some other people have been doing a little bit of hyperparameter research and also talking to Bergstra, and we're working on some fun stuff that we'll probably be talking about in the future once we summarize our results. And we have this Total Good hyperparameter optimization repo up that people can check up on, and we also love more pull requests and authors and all that good stuff. So I have a bibliography of stuff I used. This presentation was made using IPython and React. And feel free to grab it from my GitHub, which I put at the front. Anyway, that's my talk. Any questions?
Can we throw a comment out?
What?
Awesome. The gradient descent was the breakthrough that enabled them enabled them to go to multiple layers. The MLP came from realizing that, oh man, if we use a sigma here instead of a on or off, we can take derivative, and if we can take derivative, we can see the gradient descent in one pass backwards, which enabled them to do the backprop algorithm, which enabled MLPs to exist.
Oh, really? Okay. I didn't know that. That's cool.
Yeah, you're absolutely right. It's one of the things I wanted to cover, but never got around to understanding fully myself, so I couldn't explain it.
I just tested, and it's like, he has traced the derivative back to the neuron. I totally fucked it up, but now it's burning in my head of like this picture of neuron, like all little D's and all little things, how it traced back.
You can see, I started to dig into this, the back propagation algorithm that's on Wikipedia for the perceptron, and that's where I started to see, okay, there's a lot of places here that looks like could use some improvement, like gradient descent. What you also mentioned you want to see this time series, how you visualize time series neural nets. So I'll bring up some old work. So this is a network just like that one I was showing, where it has a